Okay, the next physical property which is associated with the motions of an object in a plane is the acceleration. So we know there are two types of acceleration. One is average acceleration, another is instantaneous acceleration. So first let us see about the average acceleration. Average acceleration of an object is defined as the ratio of the change in the velocity to the change in time interval. That is, A is equals to delta V upon delta T. Okay, okay, look. Instead of delta V, I will write delta uh, delta V x plus delta Vy in terms of these are the components of velocity. Okay, so we split the denominator. Fine. Or we can write this as equals to delta Vx times I cap. Can we do this? Yes, because this is just magnitude, this is the direction. So when you write arrow, it means you already take into account about magnitude and direction. But when you split separately magnitude and direction, then you have to write I cap and G cap. Okay, so this is in this. Okay, now what is this delta V upon delta T? Delta Vx. So delta Vx upon delta T, it means Ax, which is the accelerations along x-axis times I cap plus delta Vy upon delta T is equals to Ay, which is the acceleration along y-axis. So this is the expressions for the average velocity of a particle moving in the xy plane in terms of rectangular component. Fine? Okay. Now, when you look at this equation, we have A is equals to delta V upon delta T. So the direction of this average acceleration is determined by the directions of the change in velocity, because delta V is the change in velocity, so delta V arrow is the directions of the change in the velocity, right? So now let us look at the directions of the acceleration. The direction of the average acceleration is along the directions of the change in velocity. So to understand that, let us look at this figure number 1. So this curve here represent the path along which the particle is moving. Now, suppose at one time the particle is at this point and the directions of velocity it is along this direction. Now, as the time is going on, then the particle will reach at this point and the directions of the velocity, let's say it should be tangent to this point along this direction. Alright, so to get the directions of the change in velocity, we use a triangle law of vector addition. So what do we do here? We just take this, or we draw the same vector as this vector V, parallel in magnitude and same in direction. Okay, so we drop this line here, that is vector V, and we take this velocity V, which is in this direction, so we drop it. I think I made a mistake. This should be acting parallel, right? Parallel means something like this, right? So it should not be in this way. So it should be in. Okay. So we drop this line V arrow here, and this v dash here. Okay, touching the the tails of the two together. Now using vector of triangular vector addition, then this is the first vector v arrow, this is the second vector v dash arrow. So from the tip of the first vector we draw a vector, right, till it touches the tip of the second vector in this way. So this is my first, this is my second, so we start from the first to the second, so we get this is the change in velocity delta v. Okay, so if the change in velocity delta v is acting in this direction, then it means the direction of acceleration, it is also along this direction. So that is why if this is the change in velocity, then this would be the direction, right, parallel to this line. This would be the directions of the acceleration in this case. Okay, now in figure 2, what we have done here is we are reducing the time interval between the initial point and the final point. So as you do so, then this point P, which is right very far from this initial point, now it has come closer to this point. Okay, so at this point the directions of velocity is along this, and the directions of velocity at this point is along this direction. So again, when you drop these two lines here, then you'll get this is the change in velocity. So this change in velocity will tells you that, the directions of the change in velocity will tells you the directions of acceleration. So the directions of acceleration is here. Similarly here, we have further reduced the time interval, and this final point, it comes very close to the initial point. This is the final point, this is the initial point, so they come very close to each other, and the directions of velocity at these 2 points are shown here. And when you drop these two velocity, right, in this diagram, then you'll get this is the change in velocity. So with this direction of the change in velocity, it means the directions of acceleration also will be along this direction. Now, we come to the final picture, and in this case, the time interval delta t tends to 0. So when the time interval delta t tends to 0, what do you expect? We expect that this final point and initial point, they should be almost coincide. So that is why we have just one point here, because the time interval is so small, then these 2 points, right, or the displacement, it is almost equals to 0. So in that case, we have just one velocity at this point, and this velocity, let's say it is acting in this direction, which is tangent to the curve, and then, right, when we have just one velocity, then the acceleration should be along which direction? It should be right when the time interval it is tends to 0, then just look, this is my final velocity, and my initial my this is my initial velocity v. My final velocity, when the time interval it is very small, then again, right, the final velocity will be along this. So therefore we have just one velocity, and because with one velocity only, then the directions of the acceleration, or the directions of the change in velocity, it would be perpendicular to this line. So that is why we have that at this point the directions of acceleration is perpendicular to the velocity. If this is the velocity vector, this is the acceleration. Fine. So this acceleration which is taking place at this point is known as instantaneous acceleration. Why? Because the time interval is tending to 0. So therefore we define the instantaneous acceleration as a bar or a arrow is equals to limit delta t tends to 0 of delta v upon delta t. Or we say a bar is equals to, instead of this limit delta v upon delta t, we can write dv upon dt. So this is the acceleration, instantaneous acceleration. If you want to express this acceleration in terms of its rectangular component, then I can say this a is equals to dvx upon dt I cap plus dvj dvy upon dt j cap. Fine. I can say a arrow is equals to d dt of, instead of vx, because we have seen before, this vx is equals to dx upon dt, right, times I cap plus d dt of, instead of vy, I will write dy upon dt times j cap. Or a is equals to, now dd becomes d2x upon dt2 I cap plus d2y upon dt2 j cap. So this is also the other way of expressing the instantaneous acceleration, either this or this. Okay, so these are about the acceleration average and instantaneous acceleration, as well as its direction.